7.3, and we are going to be looking at some of the popular operational amplifier applications. Op-amps are used in a wide variety of applications in electronics. Some of the more common applications are as a voltage follower, selective inversion circuit, current to voltage converter, active rectifier, integrator, a whole wide variety of filters, and a voltage comparator. This is hardly a complete list. In fact, we have an entire quarter of curriculum at NSCC where we do nothing but study the various applications that are used with operational amplifiers and integrated circuits. First one we're going to look at is a voltage follower. Since the entire output is fed back, gain equals 1. And so here we have an input to the non-inverting input, and notice the entire output is fed back, so A is going to equal 1 in this case. And this is akin to what we looked at with an emitter follower. Remember, we had the emitter follower look kind of like this, and we had an output that came out right here, and the input looked just like the output, and they were basically the same size. The value was that it stepped up output impedance, or excuse me, stepped it way down, and so that's what this is going. In fact, these have when you get into the formalized calculations for these have output impedance that are just tiny fractions of an ohm. They're very, very small. If you use the formula, this is the formula for gain for a non-inverting amp. Would be RF over R1 divided by 1, and there's no RF component, so it would be 0, and the R1 component, it would be the input impedance of the op-amp, which is infinity, so 0 over infinity is 0 plus 1. That would give us the gain of 1. And voltage followers have ultimately infinite input impedance, exceptionally low output impedance, no phase inversion, and unity voltage gain, which means gain is 1. Then we have a selective inversion circuit. Since the op-amp has an inverted and a non-inverted input, by selecting one pit or input or the other, the user can choose the desired output. And so in this case, if you have your op-amp and you had the positive or the negative, and you had a switch over here, and you could choose to switch on this one or this one. You could choose to either have your input go this way or have your input go this way. It's not your text has an actual circuit. Then a current to voltage converter, and this is, let's see, your text has a picture of a transducer that converts pressure to current, and here we have an actual use of one of these. This transducer measures applied pressure applied to a braking system. The output voltage will be proportional to the applied pressure, and so here we have this transducer. Remember what a transducer does? It converts one form of energy into another. So in this case, it's taking air pressure and it's converting it into a current. Now in this case, that current is being fed into this op-amp. Remember, no current goes into the op-amp. All the current goes through here. And so this will be converted into a proportional voltage. And so that would be typically in this type of a situation, that voltage would be sent to monitoring equipment that would monitor the pressure that's being used in this system. Then an active rectifier. This is another use of op-amps. And in this circuit, this is fairly straightforward. There's a lot of lines here. You come in here with our input. It's fed into the non-inverting. This line here is not an input. This is the line that goes over to the oscope to see what we're looking at. And so the input comes in. It's very much like a voltage follower. The input is fed back to the input. And we have this diode right here. So here we have an input signal coming in. The same input signal goes out. It's just that the diode will only conduct on the positive alterations of that signal. On the negative, it will shut off, and you'll see your output here. Here we see on the positive, you have the signal. On the input, is cut off, and so we have rectification. And this is a simulation. This is from the multi-sim simulation. And something I thought I might bring to your attention here, you'll notice that the output is, in fact, the input and the output are about 169 millivolts, but you'll notice that the input is 120 millivolts. And when you're using electronics workbench and you use some of these voltage sources, oftentimes the voltage source, they're not in peak, they are in RMS. And so you look at this and you look at your output and you think, well, what in the world's going on here? So what you'll need to do is to make the conversion. And so what we would do, we say 120, let's see, 120 exponent minus 3, that is in millivolts, and we would divide that by 0.707, and there we would have 169, and so that coincides with the reading that we have on our oscope. And so let's see, that that is going to conclude this particular session. We've looked at just a few of the applications. We've looked at the active rectifier, the current to voltage converter, commonly used with transducers, the selective inversion circuit, and the voltage follower. And we're going to look at more of these in the next sections.